Hello, everyone. Thank you for this presentation. So my name is Ouafae KARMOUDA. I'm a PhD second year student at the CRISTAL laboratory of the University of Lille. I'm supervised by Rémi Boyer and Jérémy Boulanger. First, I would like to thank you for giving me this opportunity to present our work inside speeding up of kernel-based learning for higher-order tensors. So in this presentation, I will first introduce some basics of support vector machines and kernel methods for vectorial data. Then, since we are interested in support vector machines and kernel methods for high-order tensors, I will present some necessary background in tensor algebra. Once I have done this, I will present a kernel-based framework to tensorial data analysis, which is the method of the state of the art. Then I will present our proposed method named FAKSETT for fast kernel subspace estimation based on Tensor-Train Decomposition. Next, I will show some numerical experiments to illustrate the method of the state of the art and the FAKSETT method. So first of all, support vector machines is a powerful supervised learning algorithm that is widely used in several machine learning contexts, such as in face detection, text categorization, image, or handwritten recognition. Support vector machines aim to learn how to separate different groups or classes by finding hyperplanes, which will be the decision boundaries between different classes. And support vector machines assume that the data set is linear separable. But what does this mean? So if we look at this example of data set where we have two classes, the red squares and the blue circles, this data set is described by two features of variables x1 and x2. So this data set is linearly separable because we can find a hyperplane, a line in this case, such that all the data that belongs to a particular class belongs to one side of the hyperplane. So actually there exists an infinite number of lines that can separate these two classes, but we wish to find the optimal hyperplane that will be efficient in predicting the new the labels of the new data and making a good and accurate classification predictions. So support vector machines help us finding the optimal hyperplane that can separate these two classes by finding or by maximizing the margin, which is the distance or the shortest distance between the hyperplane and the nearest data points. And to find this optimal hyperplane, support vector machines solve a quadratic and constrained optimization problem where the different inner products between data samples will be required. But unfortunately, in the real world, not all the data sets are linearly separable. This is the case of this example where this data set is not linearly separable because we can't find a hyperplane that can separate the blue points from the red points. So the question here is, can we still use support vector machines to solve this classification problem? Well, the answer is yes, by the means of what we call the kernel methods. So the idea is to project the data points that lie in this input space by the means of an implicit function phi into a new space, which is a higher dimensional space called the feature space, where the goal is the data set becomes linearly separable in this feature space. However, the operations in this feature space, because it's a higher dimensional space, will lead to extremely and high impractical computational costs. But the good news is that due to a very interesting property of kernel methods, which is called by the kernel trick, and because we only need what we all need is just the inner products between the projected data samples in this feature space. So these inner products are given by a symmetric and semi-definite positive function, which is called the kernel function. Well, there are different kernel functions, and the most popular ones are the radius basis function kernel, which is given by this expression that uses the Euclidean distance between the data samples. We also have the polynomial kernel of degree d, where the constant c, d, and gamma are just hyperparameters of these kernel functions. So now we want to use this powerful supervised learning algorithm for data that needs several dimensions to be described. This is the case of hyperspectral images, particularly RGB images. Color videos, for example, need full dimensions to be represented, or images coming from the functional magnetic resonance imaging need full dimensions to be presented. So the question is, how can we use the kernel methods and support vector machines for this kind of data? Well, one can think about just flattening the data and use classical support vector machines. So this idea has two main disadvantages. The first one, when we flatten the data, the computational costs with these huge vectors will be prohibitive. Furthermore, the multidimensional structure of the data will be completely destroyed. So our aim is we are interested in methods, in kernel methods that can preserve this multidimensional structure of data tensors. So before going further in this idea, I will first present some background in tensor algebra. So in an algebraic view, a tensor is just a multidimensional array. So we already know some examples of tensors because vectors are just one-dimensional tensors, matrices are two-dimensional tensors, and three-dimensional tensors can be represented as cubes. But when the dimension gets higher, we get more difficulty to present these tensors. Let's talk now about fibers and slices of tensor. A fiber is just a higher generalization of a matrix columns and matrix rows for a tensor. For example, for a third-order tensor, we can talk about column fibers, row fibers, and tube fibers. While slices are obtained by fixing all the dimensions except two. For example, for a third-order tensor, if we fix the first dimension, we get the horizontal slices. If we fix the second dimension, we get the lateral slices. And if we fix the third dimension, we get the frontal slices. So given a tensor, we can have a matrix representation of this tensor. So for a tensor of order n, we can have n representations, or what we're going to call by n foldings of this tensor. For example, for a third-order tensor, we can have three n foldings. The first one is obtained by stacking in the resulting matrix, in the columns of the resulting matrix, the columns of this tensor. And the second n folding, the columns of the second unfolding are obtained by stacking the lines of this tensor. And the third unfolding is obtained by stacking in its columns the three mode fibers of the tensor. Now I will present the n-mode multiplication, tensor n-mode multiplication, which is an operation between a tensor and a matrix. So if we have a tensor X of order Q with dimensions I1, I2 until IQ, and the matrix U of size G by IN, where IN is one of these dimensions of X, the n-mode products will be denoted by X times NU, and the resulting tensor Y will be of size I1 until IN minus 1 G IN plus 1 IN, where the idea is the n-mode fiber of Y is obtained by multiplying the n-mode fiber of X by the matrix U. This idea can be expressed equivalently in terms of unfolded tensors. So this tensor n-mode multiplication implies that the n-mode unfolding of Y is given by multiplication of the n-mode multiplication of n-mode unfolding of X by the matrix U from the left. For example, to obtain the second mode multiplication of a tensor X of order 3 by the matrix B, it implies to multiply each row of the tensor X by the matrix B to find the second mode unfolding of Y. So now, just like for matrices, where we have very interesting matrix decompositions, such as the single value decomposition, which is a very common and widely used tool in different applications, and particularly in machine learning, we would like to have an analog decomposition for high-order tensors. So here I will present the higher-order SVD, or higher-order single value decomposition, which can be seen as one of the generalizations of the single value decomposition for higher-order tensors. So if we have a tensor X of order Q, its higher-order SVD is given by a tensor J multiplied by a matrix UQ over each mode Q, where the matrix UQ is called the Q-mode singular matrix of size IQ by TQ, where TQ are called the multilinear ranks of X, and it's actually an orthonormal matrix. And J is a tensor of the same order as X and with dimensions T1 until TQ, which are smaller or equal to IQ. So in order to compute this higher order single value decomposition, each matrix UQ can be found by computing the left singular matrix of the Q-mode matrix unfolding. So in order to compute this decomposition, we need to compute Q singular value decompositions that are related to each Q-mode matrix unfolding. So these matrices, the Q-mode matrix unfolding are of size IQ, and the second dimension will be the product of all the remaining dimensions. So the computation of this tensor decomposition will lead to compute singular value decompositions for matrices of larger dimensions. And if we call the T the maximum multilinear is equal to maximum of multilinear ranks T1 and TQ, the complexity of the higher order single value decomposition will grow linearly and exponentially with respect to the order of the tensor. And if we want to compute this core tensor that can be seen as a compressed way of X, we can just bring these matrix to the left side, transpose, and compute J using the expression given in 2. So here we have an illustration of the higher order single value decomposition of a third order tensor of multilinear rank R1, R2, and R3. So here we have the core tensor, and here we have 3 factor matrices. So by construction, the R1 first vectors of the first factor matrix form an orthonormal basis for the Conan space, and the remaining vectors form an orthonormal basis for the orthogonal complement of the Conan space. The same thing is true for the other Q mode space, which means that the RQ first vectors of each Q mode unfolding will form an orthonormal basis for the Q mode space. So now, based on what we just have seen, the question is, how can we define a similarity measure based on the multidimensional structure of the input tensors? One possible answer is just to look at the input tensor as the collection of linear subspaces coming from each unfolding or matricization. Then The idea is to look for how to define a kernel between these linear subspaces that lie on what we call by a Grassmann manifold. So what is a Grassmann manifold? A Grassmann manifold depends on two integers, n and k, and is the set of subspaces of Rn of dimension k, which means the set of subspaces spanned by k vectors of length n that we put in a matrix M, that is full rank. This is a full rank k. And if we change the basis vectors of this subspace, we clearly change the matrix M, but we will be able to reconstruct the same subspace. So that's clear, and this is a very interesting property that we'll be using just later. For example, G31 is the Grassmann manifold that contains the set of subspaces of dimension 1, which means lines, in the space. So now that we have all the ingredients, we're going to see how we can define a kernel between two tensors as presented in this paper. So the first step is to consider the higher-order singular value decomposition of two tensors, x and y. So here we have u1 until uq, the q factor matrices of x. v1 until vq are the factor matrices obtained by doing a higher-order singular value decomposition of y. And the idea presented, proposed in this paper is just to look for the subkernels between the subspaces spanned by the factors uq and vq in each mode q, and then do the products over q of these subkernels to define a kernel between x and y, which will remain a kernel if the k-tailed are kernels, because the product of two kernels is still a kernel. So these elements, which means the subspaces spanned by uq and vq, are in the Grassmann manifold GIQ-TQ, which is the set of subspaces of RIQ of dimensions TQ. And the kernel k-tilde here is defined by a radius basis kernel function, or what we call by Gaussian kernel, in the Grassmann manifold, where we use a projection metric as a distance between the subspaces spanned by uq and vq, which is given by the Frobenius norm squared of the difference between the projectors on these subspaces. So the choice of this distance is not arbitrary, because this distance gives rise to a semi-definite positive kernel that is an interesting property in order to use support vector machines with kernel methods. So now this idea is very interesting, since it preserves the multidimensional structure of the input data tensors and gives a valid kernel. However, the computational cost of the higher-order singular value decomposition is very expensive, especially when the order of the tensor becomes high. So our objective is to reduce the complexity of this method, that we call of this native method, by using an algebraic equivalence between the higher-order singular value decomposition and a new decomposition called the Tensor-Train Decomposition. So first, we're going to define what is the Tensor-Train Decomposition. So the main idea of this decomposition for a tensor x over the d is to break this tensor into d minus 2 tensors of lower order, of order 3, and two matrices, J1 and Jd. So here we have the dimensions of the tensor, and R1 until Rd minus 1 are called the TT ranks of x. So elements-wise, we say that a tensor x follows a tensor train model if each of its entries is given by the sum over the TT ranks of the product of these elements. So, so in order to reduce the complexity of the higher order singular value decomposition of X, which is given by these decompositions, where U1, UQ are the factor matrices, we're going to compute the tensor-train decomposition of X, which is given by this expression. So this expression is the notation of this means that each element can be written as this expression. And why we choose the tensor-train decomposition? Because these decomposition help us mitigate the curse of dimensionality. Well, it will help us reduce the complexity of the higher order single value decomposition by an order of Q. So when the order of the tensors gets higher, there will be a significant reduce of computational time using tensor-train decomposition. And the most interesting property that will allow us to speed up the native method just presented earlier is that because in the native method, all we need is the subspaces spanned by these factors UQ. And the tensor-train decomposition gives us this interesting property, since we have that for Q between 2 and Q minus 1, the factors UQ and the second unfolding of these core tensors GQ span the same subspaces. Furthermore, U1 and J1 span the same subspaces, and the same thing is true for the matrix UQ and GQ transpose. So here we have an example where all the multilinear ranks are equal to 2. So here we have the matrix UQ that contains 2 vectors, and here the second unfolding of the core tensor GQ that contains 2 vectors too. So here we see that they span the same subspaces. This key property is deduced from this main theorem, which gives the equivalence between the tensor-train decomposition and the higher order singular value decomposition. So the main idea of this theorem is that if we have a tensor X that follows a higher order singular value decomposition of multilinear ranks T1 until TQ, we can recover the core tensors of its tensor-train decomposition using the Q factors U1 until UQ that we get from this higher order single value decomposition. So now we are ready to present the proposed method called FAKSETT, which aim to speed up the native method. So the first step is to consider the tensor-train decomposition of X and Y, given here. So we have G2, G1, G2, GQ minus 1, GQ are the core tensors of X. G1 prime, G2 prime until GQ prime are the core tensors of the tensor Y. So we're going to compute the subkernels between the subspaces spanned by the second unfolding of each core tensor for each mode, because because these the second unfolding of these core tensors span the same subspaces as the factors of the higher order single value decomposition. And then we define, as in the native method, the kernel between X and Y just as the product of these subkernels, where we also use the kernel Gaussian kernel, which is defined between the subspace spanned by the second unfolding of GQ and the subspace spanned by the second unfolding of GQ prime, by the Gaussian kernel, where we use the projection metric as a distance between these subspaces in order to have a semi-definite positive kernel function that will lead to a valid kernel for K tilde and then a valid kernel for kernel K between the tensors X and Y. So our hope is that this FAKSETT method will help us reaching the same accuracy scores and classification performance just like the native method, and reducing the computational time for finding the factors by tensor-train decomposition instead of the higher order singular value decomposition. So in order to see, to illustrate these methods, we have two real datasets. The first one is called the UCF11 dataset that is composed of videos. So these videos can be seen as a full order tensor, where the first dimension contains the number of its frames, and the three dimensions are the dimensions of the frames. We choose two classes to classify from these datasets. Each class contains 109 tensors, and we vary the training sets, the percentage of training sets, and the multilinear ranks to compute the higher order single value decomposition for native method. And here we compare the classification accuracy between FAKSETT and the native method. So what we remark in this table is that the FAKSETT method can reach very close accuracy scores, like the native method. So the second data set that we're going to consider is the extended Yale dataset. It contains images of 2011 human subjects, where these images are taken in different poses and different illuminations. So we choose three classes for this dataset, and we'll reorganize these images in a tensor of order 4, where the first dimension is the number of poses. Here, the two dimensions correspond to the dimension of the images, and the fourth dimension is reserved to the number of illuminations. So here, if we vary the percentage of the training sets and the multilinear ranks for computing the higher order single value decomposition, here we have the classification performance of both of the methods. So we clearly see that both of the methods reach very high accuracy score to classify these datasets. However, in terms of computational time, so here we have the time on seconds consumed to compute the factors that we need to compute the kernels, and here the time to consume to compute higher order single value decomposition. So we've clearly noticed that the FAKSETT method help us reducing significantly the computational time compared to the native method. And this is just in the case, so even if we have only tensors of order q equal to 4, so if we have tensors of higher order, the gain time will be more noticeable. So to conclude, we have presented a method named FAKSETT, or fast kernel subspace estimation based on Tensor-Train Decomposition. That reduces significantly the running time for the computation of the factors, despite with working with q equal 4. So we call this, so we show that the FAKSETT reduces, reaches a very small, similar accuracy scores as the native method, with a running time considerably reduced on two real datasets. So thank you for attention, and if we have questions, don't